This is part 2 because I couldn't put 0, first, and second order all in the same YouTube video. So this describes the third type, the second order reaction. Again, you cannot tell from the chemical equation. The rate looks just like it did in the beginning of the chapter. The only change we have is you can see the number 2 there denoting a second order. Once again, we take our equations and we equal them. We integrate them using calculus. Your textbook ignores the A, and we rearrange for graphing. So we show that in the last video. Now, how will you do a problem? Well, if you're looking at data, now you're going to be making a decision between the first order and the second order. I put my first order equation down, put my second order equation down. Here you can see for the first order, I have ln of what's on the y-axis. Here you can see for the second order, I have 1 over what's on the y-axis. And they used a different example. So again, here's a chemical equation. There's my hard data. There's my time versus concentration. And what I had to do is I had to work up the data the 3 different ways. This would be the 0, this would be the first, this would be the second. I don't know what your lab looks like this term, but in the old days, you would be doing an experiment in the lab to collect data and to analyze it. How can I tell what is right? Well, here I have a curve, so it is not first order. Here I have a line, so it is second order. So it's really easy to do. Do your points always follow in a perfect line? Absolutely not. But they should make a perfect line. Can't have that happen on exams. What you could have is a word problem. And I said, using the second order equation. Here it says verbally, this is second order in NOBR, which says one should use that integrated rate law. Just like before, I'm going to write down my data. K is 0.810, molarity minus 1 second minus 1. It says we start with 4.00 times 10 to the 3rd molar, NOBR. And how many seconds does it take? We want to know what is our time, because what we are going to do is we are going to use up 1.50 times 10 to the molar NOBR. Notice this is not our concentration at time t. We will find that by taking our original concentration. We will subtract from that what we have used. So this is our used. This is our initial, and what we will come up with is how much actually was left. Okay, this was our final, so this would be our concentration at time t. And again, I learned last semester, get ready before you come to class. So what I did is I took my concentration at time t, I took my rate constant, there we have it right here, and I took my initial concentration. What we're solving for in this case is t. So again, this is math. We come up with 400 equals 0.810 times t plus 250. As we rearrange things, we come up with t is equal to 185 seconds. Again, this is the expectation that you will do. In the past, they've provided all the integrated rate laws. All you have to do is read the problem, substitute it in, and solve. So let's just step back for a second. Graphing with the integrated rate equation. Each order has a specific y-axis label. Now, in the past, when students could not consult their notes, they went crazy. You can consult your notes. Please take the appropriate notes to your exam. The reaction will have that order when you have a straight line. Notice we have a negative slope here, and a negative slope here, and a positive slope. Math is necessary to do things in science, and I guess this is a perfect example. I just put everything on one slide. All right, what else do we have here? Well, we talked about half-life, and let's kind of look at the second one. This is where you think it through. If you begin with 10 molar, 1 half-life is 5, 2 half-lives is 2.5, 3 half-lives is 1.25. But what if they give you a plot? Well, over here, it starts at 150. half of it is 75. So you read over to the line and you drop down onto the x-axis. For another half-life, you go from 75 down to half of that, 37.5. You read over and you drop it down. So those are using a plot. Here's another one where you actually think through it, but what you have on your exam are some word problems. And again, I would normally write it myself, but I've learned one's crunch for time in these things. I have a first order and I have a second order. First order expression, t1/2 is 0.693 over k. I substitute in my value of k. I hate to write this, but I will say easy points. This is also radioactive decay. So we're going to run into this as we get through this course and we talk about nuclear reactions. A lot of biological processes also are first order overall. What about second order? Well, there's an equation for that. And all you need to do is put in your K, put in your concentration, bingo, there is the answer. So I will also say, I shouldn't say this, again, easy points. And you get to bring everything in with you. Label these things and use them during your exam. What do I have to summarize what's in this section? How will you know which equation to use? This has come up so many times teaching this material. Well, if I'm given a rate and concentration, I know it's a rate law problem. How will I know it's an integrated rate law problem? Someone's going to give me an actual time, whatever that number is, and a concentration. So you need to choose the appropriate integrated rate law when you're given time. The problem could explicitly state the order of the reaction, then you know your y is equal to mx plus b form. They could tell you the rate law and recognize that, because often students say, I don't know where it came from. Well, all it is rate is equal to k, and there can be a concentration. Or they can tell you the units of K. And we did this in an earlier section where we worked through and showed how you get the units of K. This is overwhelming if you've never seen it before, but please take a couple of days to let it sink in, and I know you'll be successful.